In this video, I'm going to do a rather involved proof of the first composite argument property. That property is really important because it's used to prove many other properties. So stick with me and see if you can follow along. First of all, could I find this question here? Could I find cosine of 15 degrees without using my calculator? Well, I would need to use special angles that I knew without having to use the calculator, and I could possibly use angles 45 and 30. And so the question is cosine of 45 degrees minus 30 degrees equal to cosine of 45 minus cosine of 30? So is the cosine of the quantity equal to the difference of the two cosines? So recalling from special triangles, and we'll review these a little bit later in the notes, cosine of 45 is the square root of 2 over 2, and cosine of 30 is the square root of 3 over 2. So I'm going to check on my calculator to see if cosine of 15, which is 45 minus 30, is equal to the difference of these two trig values. And if I check, I see here's cosine of 15 is 0.9659, but if I subtract these two trig values, cosine of 30 minus cosine of 45, not only do I not get cosine of 15, I don't even get a positive trig value. So clearly that is not the way to estimate cosine of 15. So we're going to look back and see a way to do it. In order to do this proof, I have to remember a couple things. The Pythagorean Theorem is one of them. So if I have a point x1, y1 and a point x2, y2, I can find the distance between them based on the Pythagorean Theorem. This horizontal leg of this right triangle tells me the difference in the x-coordinates. The vertical leg shows the difference in the y-coordinates of the 2 points. Using the Pythagorean Theorem, the difference in the x-coordinate squared plus the difference in the y-coordinate squared will equal this diagonal distance squared. So in order to find the distance, then I take the square root of the difference in the x squareds and the difference in the y squareds. That's one piece of information I'm going to need. Secondly, recall that when you have a unit circle, a circle with radius 1, that the cosine of any angle is going to be x over 1, which is just x, and the sine of any angle is going to be y over 1, which is just y. So when I name this point xy, I can also name this point as cosine theta sine of theta. So the coordinates of the points on the unit circle are the cosine and sine of each angle. So that's important to remember. Now the next thing I'm going to do is set up, I want to figure out what cosine A minus B does equal, so I'm going to set up an angle A and an angle B, and then between them the angle A minus B. So angle A is this red angle here, and I can name the coordinates of its point as it intersects the unit circle cosine A sine A, based on what I talked about earlier. I can name angle B right here. I can name the coordinates of the point that intersects the unit circle here as cosine B sine B. I'm also going to say that this distance d is the distance between these 2 points. So I can name this distance using the distance formula. I can say cosine A minus cosine B squared plus sine A minus sine B squared, and take the square root of that whole thing, and that's this distance right here. Now, the difference between angle A and angle B is angle A minus B, which is this angle marked in black. And if I take this angle, angle A minus B, and move it over here and reposition it so that one side of it is on the x-axis, I still have the same distance d here, but I can rename the endpoints. This point on the x-axis would be the point 1, 0, because this circle has a radius of 1. And this point here would be cosine of the angle A minus B, sine of the angle A minus B. So I can also calculate the distance between these points using this radical here. Cosine A minus B minus 1 squared, that's the difference in the two x values squared, plus sine of A minus B minus 0 squared, that's the difference in the two y values squared. And I'm going to then square both sides of this equation to get rid of the radical. So because these two distances d are equal to each other, then both these forms of the distance formula, both these expressions of the distance formula will give me the same distance. So that's the basis of setting up this proof. And then we're going to recall one other piece of information. I shrunk this down so it would be out of the way earlier. But we're going to recall that if we have the quantity a minus b squared, it multiplies out to a squared minus 2ab plus b squared. And this then leads us to all the algebra in the proof. So I'm going to multiply out this particular binomial, and I get cosine squared a minus 2 cosine a cosine b plus cosine squared b. I'm going to multiply out this part underlined in blue and get sine squared a minus 2 sine a sine b plus sine squared b. That's the whole left-hand side of the equation. Then I'm going to multiply out this binomial underlined in purple and get cosine squared of the quantity a minus b minus 2 cosine a minus b plus 1. And then lastly, sine a minus b minus 0 squared is just sine squared of a minus b. Now, I can simplify this by noticing that I have a cosine squared of a and a sine squared of a. And based on the Pythagorean property, cosine squared of a plus sine squared of a is 1. Cosine squared of b plus sine squared of b is also equal to 1. So I have 1 plus 1, which is 2, minus 2 cosine a cosine b minus 2 sine a sine b. So that's what I have here, 2 minus 2 cosine a cosine b minus 2 sine a sine b. On the right-hand side, cosine squared of a minus b plus sine squared of a minus b equal 1. I have another 1 here, which gives me 2 minus 2 cosine a minus b. Next, I will subtract 2 from both sides, which eliminates the constant on both sides, and then I'll divide both sides by negative 2. That leaves me with cosine a cosine b plus sine a sine b equals to cosine a minus b. And that's my first composite argument property. Now we're going to return to the problem that we had up above, which is how do I find cosine of 15 using angles that I know that are special angles? Well, I can go back to saying cosine of 15 degrees is cosine of 45 degrees minus 30 degrees. But this is my a minus b. So cosine a minus b is cosine a cosine b plus sine a sine b. So I'm going to write cosine 45 plus cosine 30, or times cosine 30, plus sine 45 times sine of 30. Using my special triangles shown below, with these trig values identified, and you might want to pause and take a look at those, make sure you understand where all those came from, I can substitute square root of 2 over 2 for cosine 45, square root of 3 over 2 for cosine 30, square root of 2 over 2 for sine of 45, and 1/2 from sine of 30. When I multiply these two, I get square root of 6 over 4. When I multiply these two, I get square root of 2 over 4. I could also write that as square root of 6 plus square root of 2 all over 4, but I cannot add these together because they are not like radicals. Now let's go back to the calculator and check to see if this quantity is actually equal to cosine of 15. You can see here I've entered square root of 6 plus the square root of 2 all over 4, calculated, and it does equal cosine of 15. So that is a true statement. We've shown it algebraically and geometrically and verified it then numerically that that is a trig property. The next video then will show how we use that property to derive the other composite argument properties.